This is an exponential decay problem, and it's a really common type of problem, a half-life problem. So just in case you've never heard of half-life before, if you haven't taken Math 30, you've never heard of it, probably. Actually, I don't know, maybe in chemistry or something. But a half-life is basically means that when we're talking about especially radioactive materials, but also other things too, like fossils and stuff, a half-life means that the half-life is the amount of time it takes for half of the original amount to be remaining. So if I say the half-life is 50 years, that means after 50 years, there will be half of whatever was there before. Okay? So if I start at 100%, after 50 years, there'd be 50%. Then after another 50 years, there'd be 25%, because half of 50. Then another 50 years would be 12.5%, so forth. Okay? So here we're told that the half-life of some radioactive substance is 20 days, and there are 5 grams presently. So if I made like a table for this, I mean, we're going to talk about equations, but just imagine like simply, because sometimes the equations trick people up a little bit, but if we're just thinking of this, it means that after 0 days, there's 5 grams. After 20 days, there'd be 2.5. After 40 days, there'd be 1.25, and so forth. Okay, we just keep going. So after 60 days, there'd be half of 1.25, and so forth. You know, it just keeps going. That's how half-life works. So every that many days, there's half left. So the formula for this makes a lot of sense intuitively if you try to understand it. It's the amount, the final amount is equal to the initial amount times 1/2 to the power of time over half-life. Oops. Trying to like make my tea better. Okay, so time over half-life. So this makes sense because you think about like I'm going to take 5, which is my initial amount, and I'm going to take it times it by 1/2, and then this is the part where people usually forget. They're like they can't remember if it's multiplication or divide, and they're just trying to memorize it. But it makes sense. Like if you think about it, if it's been 60 days in total, if that's what your x value is, then 60 divided by 20 is 3, and it's being halved 3 times. Okay, that's what you're trying to think of. Like this entire exponent should be how many times it should be how many times it's going to be halved. So how many half-lives have there been? Okay, it makes a lot of sense. So here, when it asks when will there be only 1 gram remaining, okay, I know that my A naught is 5, because that's the initial amount. That's what the naught usually means initial, right? In like physics and in math, usually that little O means initial. Okay, then 1/2. And the half too, it makes sense as well, right? Like we talked about yesterday, if you're growing by 10%, it's 1 plus 10, right? And then you get 1.1. If it's shrinking by 50%, which is what's happening here, we're halving it. It's shrinking by 50%. Think of that as being 1 minus 0.5. Well, 1 minus 0.5 is 1/2. So that's why it's 1/2 here. Okay, and then t, which is time, over h, which is 20. So there's only one spot. I can't really get that, but that's okay. There's only one spot for the 1 to go. It's right there. Okay, so we're trying to figure out, on the other side here, so we're trying to figure out what is the value of t so that 5 times 1/2 to the power of t over 20 is equal to 1. Okay, that's what we're trying to figure out. Okay, so it's pretty straightforward, I think. Now here, there are a couple different ways to solve this. You would either have to do it using your graphing calculator. So if I gave you a graphing calculator, what would be the easiest way to solve this? If you had a calculator. No. Yeah. Okay, so don't just keep putting in values. That would take a long time, right? But any equation that you're given ever, if you have a graphing calculator, is solvable just using graphs. So if you put this into y1 and this into y2, or the other way around, it doesn't matter. You put one side of the equation into one graph, the other side of the equation into the other graph, and what do you find? Yeah, look for the intersect. Okay, and that will let you find the answer to any equation. Okay, so if you have your calculator, that's the way you do it. Now say you don't have your calculator. And say your life has like gone into shambles and somehow you ended up in a scenario where you don't have a graphing calculator. I can't imagine that situation myself because I always have one. But if it did happen, okay, then what would you have to use? Someone who's taken Math 30. Logs. You would have to use logarithms. Okay, so that's what we're going to be spending most of our time today working on. I added a couple slides because I want to do a little more practice with logs than I usually do. In large part because some of the people in this room probably have never seen logs, and I feel bad for them because their life can't be full yet. Your life only really fills out once you've seen logs. Okay, so here, logs are, if you don't know, logs are the opposite of exponents. Okay, they're the inverse of exponents. The same way that like multiplication is the inverse of division, logs are the opposite of exponents. So we can use them to solve something when there's an x in the exponent. Okay, everyone with me so far? And I'm not actually going to show how to do it here because I want to go into some basic stuff first. Okay, so I added a couple slides, like I said. Yeah, I'll come. Okay. Oh, this is about E. This stuff about E. Okay, so here, guys, this slide, if you look for it and find it, it's talking about the number E. So we talked about it just very briefly the other day. E is called Euler's coefficient or Euler's number. It's named after Leonard Euler, who was a very famous mathematician. It's similar to pi. It's just like it's an irrational number that gets used a lot. It gets used a lot in a lot of real life applications, like in business in particular. It gets used a lot when we're talking about continuous interest. It gets used. So it's just a number that you should be familiar with. It's just a decimal. Like if you type it into your calculator, so on your calculator, it's right under pi. So instead of like going second pi, it's second E. You can see it's like 2.719, I think. 18. Yeah, it keeps going forever, just like pi does. So it's just another number. So don't freak out when you see it. So it says here many phenomena are best modeled by an exponential function whose base is the famous number E. Okay, Euler's number. So if you look at it, one of the definitions for E, there's a lot of definitions for E. Like pi is the definition. The definition of pi is usually something about like it's like the ratio between the circumference of a circle and the diameter or something like that. Here, E, one of the definitions of it is that it's this function. So if we graph that function, 1 plus 1 over x to the power of x, if you graph it and you look what happens when x gets very, very large. So if we like make x a very large number, like if we make x 700 and you check to see what this gives you, we can even just do that by typing into our calculator. If we just type into our calculator, ooh, whoops. My God, what's happening here? Okay, 1 plus 1 over 700 to the power of 700. If you just do that even, so try typing that in, what do you get? Yeah, don't even use your graph, just if you just type that into like the main screen of your calculator, what do you get?
On the graph, it's a straight line.
It looks like a straight line. It's not a straight line, but what do you get? You get 8? E. You get that E number. Yeah, you get about 2.7, right? Okay? Ish. Okay? So the higher that number gets, so on your graph, if you do graph it, you'll probably get some kind of looking, I don't know, graph. Does it go up like this? Is it going up and then down? I mean, at some point, it's not a straight line.
It's like,
so it's,
yeah.
Okay, so you get one of these looking things, and it keeps going, and the idea here is that the line that it's getting closer and closer to, it looks like a straight line, but it's not. It's just getting closer and closer and closer to that E. Okay, it's getting like, as it goes on, that asymptote, the horizontal asymptote there is at E. So that's one of the definitions. So the exponential functions, e to the power of x and e to the negative x, are often used with growth and decay. For instance, compound interest compounded continuously uses the model p times e to the power of rt. So you don't need to know that formula necessarily. I would give it to you if I gave you a question, but just so you're going to see this number come up a lot. Like e to the power of x is a function that gets used in calculus like constantly. So just knowing that it exists, but it's really just a number. It's like the same thing as like 5 to the power of x, right? It's just a special number, e. So I want to panic when you see it. Okay. So logs and functions here. We're going to be talking about inverses for a few minutes. One thing is the phrase 1 to 1. It's something, if you've taken Math 30, you would have heard before, even if you don't remember. But 1 to 1 means that a function is not only a function, like, because function means that it passes the vertical line test. 1 to 1 means that it also would pass the horizontal line test. Okay, so that there's nowhere that if I draw a horizontal line, it would cross the graph twice. So like when we talked about functions, I remember Ryan knew it was like each x value only has one y value. If it's 1 to 1, you can say the opposite as well. You can say that each y value only has one x value. So it's that it's only goes one way. So for instance here, this one, the cubic function is 1 to 1 because there's nowhere that if I draw a horizontal line, it would touch twice. And there's nowhere that if I drew a vertical line, it would touch twice. Okay, now this quadratic function here is not 1 to 1 because obviously I could draw a horizontal line pretty much anywhere and it would touch the graph twice. Okay, is that fair? Easy enough. So this is important because it's actually probably more important than in 30-1 to be honest, because they like to ask questions about whether or not the inverse is going to be a function. And you can tell by this. So if a function is 1 to 1, then the inverse of that function would also be a function. If a function is not 1 to 1, then the inverse of that function would not be a function, which I know sounds very confusing, but let's just kind of take a look. About it, it's because, right, like some of you don't maybe know what inverses are yet, but an inverse is a graph where the x's and the y's have swapped. Okay, that's what an inverse is. And so all your x values become y values, all your y values become x values. And for a quadratic, like this quadratic here, the inverse of it would be like a sideways parabola. Okay? Now a sideways parabola is clearly not a function because it doesn't pass that vertical line test. But a cubic, if I did the same thing with a cubic function, honestly, I'm going to have kind of trouble with it. Actually, I think I could do it. Woo! Woo! It looked like that. That is still a function because it would pass the vertical line test. First, about doing some log.
You say the inverse, if it is 1 to 1, will be a function?
Will be a function. Okay? And if the inverse, if it's not 1 to 1, it won't be. Okay? So when you, okay? So an inverse, this is the actual definition of an inverse. Please also be familiar with the notation. So inverse of f denoted usually by f to the power of -1. That means inverse f. This notation kind of sucks because -1, as many of you know, often means 1 over that thing, right? We talked about that. I just, like Cash was using that notation in one of those problems. He had x to the power of -1. X to the power of -1 means 1 over x, right? That's not an inverse. That's like using a negative power. In this situation where you see f to the power of -1, that does not mean a negative power. That means inverse. And I know it's kind of a crappy notation, but at some point they decided to use it. Okay, so don't confuse it. F to the power of -1 is not equal to 1 over f of x. I'd say that's one of the most common mistakes I see with students making, is they think that f to the power of -1 is the same as 1 over f of x, and it's not. Okay, so f to the power of -1, or that inverse f, means that the x and the y values of our function have switched. So the other way that you see it a lot is they write f of y equals x. Okay, they like switch it around. So instead of seeing f of x equals y, you see f of y equals x. That's another way that sometimes inverse gets written. It's actually better because it's like more actually what's happening. So for instance, on a graph, if 1, 2 was on your original graph, 2, 1 would be on your inverse, okay, because they just flip. So all the points in your whole graph flip and makes a new graph. Okay, that's what happens. This is another Oh, sorry, this is a test for inverses. One easy way to tell if something's an inverse, algebraically rather than graphically, is do the composites. So do f of g and g of f. Remember, f of g, f o g like that means f of g, okay? And g of f means g of f. It just means that. If they're inverses, those are equal. Okay, so it's kind of an easy test. So here, with these ones, for instance, if I was doing this, f of x equals x cubed and g of x equals cubed root x. I mean, those are pretty clearly inverses, but let's just kind of see how this works. If I do f of g, and like inverse, like think about inverse as the same thing as when you were little, like when you were in grade 6 or 7 and you started to learn algebra, and they tell you it's inverse operations. This inverse is the same thing. Like the way that plus and minus are inverses of each other. Multiply and divide are inverses of each other. That's what we're talking about here when we're talking about inverses. Okay, so cube and cube root are inverses. So x cubed and the cube root of x are going to be inverses. But let's kind of see how it plays out. So if I do f of g here, so if I do f of g, if I do f of g, that means I'm plugging g in for x. So I'm plugging this into x cubed. So it's going to be the cube root of x cubed. So what happens when I have the cube root of x cubed? It's just x. And if I do the opposite, so if I do g of f of x, and I plug x cubed in for that x, and I have the cube root of x cubed, which is x. So since these are equal, that means that these are inverses. Okay, this is one, and obviously this one's very simple, but this is one way to test if two things are inverses. Okay, so it's not a bad test. Versus, I'm gonna go, so sometimes things look like inverses and they actually aren't. Like, it happens, so. Yeah, I'm going to show you how to actually find inverses now. This is the important part. This is the part I want you to be able to do for sure. It's a pretty simple skill. Okay, so all you do if you're asked to find the inverse, is you switch the x and the y and you solve for y. That's it. Switch the x and the y, solve for y. So with f of x equals negative 2x plus 4, you instead write it as x equals negative 2y plus 4. So see, all I did is I switched the x and the y, and then I would solve for y. So I would subtract 4 on both sides. So I get x minus 4 equals negative 2y. Then divide by negative 2. Or you could do it another way if you wanted. Okay, and so my answer here would just be y equals negative. You could just leave it like that, to be honest, or you could change it into slope-intercept form, whichever you prefer. This would be negative 1/2 x plus 2, okay, and that would be it. So there we go. There's the inverse of it. Really easy. Okay, well, I mean, when they're linear, they're really easy. These they can be much harder. Okay, now b. Okay, what would I get when I switch x and y? It's not a trick, it's going to be the same. So I switch x and y around, so x equals...
Negative bracket y minus 2 bracket squared.
Yeah. So just like that. Okay, and now it's just a matter of solving for y. Now here, be a little bit careful. Like if you were doing this, I mean, you could do it a couple different ways. You could like expand this if you wanted to, I guess, but it'd probably be a bad idea. The better thing to do is certainly to get rid of the negative first, then square root.
Don't you have to do square root first?
No. You don't. So here, when we do this, I would divide by negative 1. Okay, so I get negative x equals y minus 2 squared. Then I would square root. Now here we do have kind of an interesting thing going on. And then I would add 2 to both sides. So I'd end up with the square root of negative x plus 2 equals y. And that would be my answer. Now this is sort of an interesting situation because I would have to restrict the domain here because you can't take the square root of a negative number. So what sort of number can x be? If I'm not allowed to take the square root of a negative number, what number is x allowed to be? It has to be a negative number. So I would say x has to be less than or equal to 0. Okay? We'd have to restrict the domain there. Because if x is negative, then negative x is positive, right? It even just looks funny to have their negative x underneath the square root sign. You could change it to positive x and restrict it the other way. That would work. Okay? But yeah, so that's how you do inverses. It's pretty straightforward. And so this function y, you don't necessarily call, like here they are kind of encouraging us to call it f of negative like that way. So you could write it that way instead, like that this is f of negative 1 is negative a half x plus 2, like that. Okay, that would be correct as well. I'm not too picky about that. Logs, okay, like I said, are the opposite of an exponent. So for instance, if you have something, let's do something really straightforward. If I had something like 5 to the power of x equals 25, okay, that one I assume could figure out, okay, without needing logs. But logs is the opposite of this. So logs, what logs would be, the way I would write it is I would write log 525 equals x. These are inverses of each other, okay? So the way that generally speaking you're taught it in Math 30 or whenever you learn logs is that the base stays the base and the other two switch. Okay, that's usually what's told to people. That's, for whatever reason, is confusing to people. Okay, so we'll see some other ways to talk about it. But before we even get into that too much, but I'll show you what I mean by that. Base stays base, the other two switch. The base of a power is the big number, right? Everyone's with me on that? So this here is the base of my power, the big number. It becomes the base of my logarithm. Maybe what's confusing is that the base of the logarithm is a little number. Okay, we're changing it up. So it becomes there, and then the other two switch sides. So 25 now, because it used to be on the other side of the equal sign, goes with the log, and the x goes on the other side. Okay, that's like the official rule. Now, if you type this into your calculator, log 525, I'll teach you how if you don't know how already, it will give you the answer, which is 2. Okay? And clearly, if you looked at this, you would just know x was 2, but it would actually work. Now, what I want to get into here before we move on, because what I found last year with my 30-2 students is spending quite a bit of time on actually just evaluating logs. Seemed to help them. They got much better at logs than a lot of 30-1 students I've seen. So I was impressed with it, but it took a lot of practice. So looking at a log, I would like it if people were good enough at logs that they could just look at a simple log and evaluate it without a calculator. That is what I would like for you. Okay, so for instance, if you saw something like log 2, 8, and I'm not talking about really tricky ones, I'm talking about simple numbers, okay, I would like it if you could just look at that and tell me what the answer is. So can anyone tell me what the answer to, or the evaluation of log 2, 8 would be? 3. Okay, now, for those of you who maybe have never seen this, don't feel left out, okay, the way you're doing it, or you should be doing it, is you should be thinking 2 to the power of what? 2 to the power of what gives me 8. Okay, you're figuring out the exponent that would make that base into whatever the big number is. Okay, so here it's 3, because 2 cubed is 8. Okay, now let's look at slightly harder, but not significantly harder. If you have ones that are fractions, okay, so say I had something like, my gosh, what's happening here? Okay, log 2, 1 over 16. Does anyone have an idea of what that one would be? -4, thank you, Dash. Okay, so fractions, all you have to remember is that negative exponents make fractions. A negative exponents make the number go on the bottom. So you're like, well, 2 to the power of what is 16? It's 4. Okay, and since it's 1 over 16, it's negative 4. Is everyone okay with that? It's good so far? Okay. So far, so good. Okay, what about something like this? 1/2. Thank you, Akash. Akash is the best at logs.
Am I actually that dumb? I thought you were trying to use 2.
Okay, so fractions, similarly, okay, an exponent with a fraction is the same as a root. So if you have x to the power of 1/2, that's the same as square root of x. Okay, if you have x to the 1/3, that's the same as the cube root of x. So here, what you should be looking at is, well, okay, I know that 8 is the square root of 64. So that would be a square root, which is 1/2. Okay, that's the way you should be thinking about these things. So what I'm going to do right now is I'm just going to... I think that's probably order here, because I really just want to focus on logs first. Okay, so, yeah, just like our crappy school internet. So, just like that power law, once it catches up, if it ever does, okay, a to the x times a to the y is equal to a to the x plus y. We have logs. Logs, the rules are that if you have a log with a multiplication, it's like literally the opposite. If there's a multiplication, you can split it up into 2 logs that are adding. So it's like the opposite. Before, when you had 2 multiplications, you could put it together to add. Here, if you have them adding, you can put them together to multiply. They're just inverse rules of one another. And it's the same with the other rules. They're all really important, and I'll show you how to work with them. Maybe if I close out of here. Okay. Okay, so if we look at, there's 3 rules. Okay, there's the adding rule, that when you add, you multiply. There's the power rule, okay, which is that when you have something to a power, you can drop it down to the front. That's a really important rule. Okay, let's see. Yeah, I think that maybe helped to catch up a little bit. Okay, so that middle rule, now it's still lagging. Okay, so in the middle here, this rule is really important. When you have this power out here, you can drop it down to the front. Okay, and then finally, when it's a division, you subtract. So it's very, very similar to the power laws. I'm going to show you how I want you to use them here for this next question. Okay, well, either way, here it is. I swear I put this in here earlier. I guess not. Okay. Here. Oh, it's not up yet because it's really lagging. Maybe I'll just do it on the screen. But then you won't be able to watch it later. I'll do this one. Okay. So I'm just going to do this example with you guys about how to use these laws. Okay, so this is the way I want you to use these laws. These questions are also really common in Math 30, at least on the departmental they are. They really like them. It's them wanting you to just use these laws to like rewrite logarithms in terms of other variables. So here we have that a is log x, b is log y, and c is log z. Write the following expressions in terms of a, b, and c. So what you want to do here is you want to split these things up, and we jumped right into hard ones. I'm not doing really simple ones. But when there's a multiplication, the way you split them up is by adding. And when there's a division, the way you split them up is by subtracting. So don't overcomplicate it here. I can split this one up. That's log x squared y z cubed. I can split, that's a 3-way multiplication. So I can split it up into 3 additions. So I can split it up into log x squared plus log y plus log z cubed, like that. Okay, I can split it up like that. So once I split it up like that, now this is where I think most people make mistakes, is people are like, oh, okay, well that's a squared, b, and c cubed. But it's not, because this is not log x squared. Like there's no brackets, right? Like there's no, it's not like that. It's not log x squared. That's what a squared would look like. It's log of x squared. The brackets would not go around log x. The brackets would have to go, if you were going to use brackets, would go around x squared. Okay? So there's a difference, and they didn't appear there until just now, but now you can see what I mean. Okay? Those brackets would not be around log x. They would be around x squared, if anything. So the way that we have to simplify this is before we deal with, put the a's and the b's in, we have to deal with these powers. So the power rule, the middle rule from the last slide, is that this 2 can move down to the front, right? So instead, I can write that, and I wouldn't necessarily expect you to write down all these steps, but you write down 2 log x plus log y plus, what would the last part be? 3 log z. Okay, and then that, now I can replace my thing. So instead of 2 log x, I can write 2a. Instead of log y, I can write b. And instead of 3 log z, I can write 3c. Okay, and it's eventually going to come up, I'm sure. Okay, one day. Okay, I'm going to do the second one. Let me just check if, I think that these rules work in conjunction together. Okay. I have to talk about. Yeah, so similar, like logs and stuff, which we saw yesterday, logs and exponents are inverses the same way. Like if we graph y equals log of x, it's the inverse of y equals 10 to the power of x. So e has its own logarithm. It's on your calculator. If you look at your calculator, underneath the log button, there's ln. That's called the natural log. It gets used a ton in math and engineering and science, so that's why it has its own button. It's used so often. So when you see lnx, I find this is one of the hardest things because it's not in the Math 30 curriculum anymore, which is kind of stupid because it's really important. But anyway, ln x, if you see that, it's the same thing as log with a base of ex. Okay? It's just a shorter way to write it. Like it gets used so much that that it has its own notation. Okay, so if you want to, you could always change it. Like if you see lnx, you can change it to log with a base of e if that helps you. So for instance here, like if I'm trying to switch around here, ln x, that's just log e to the x equals 3t plus 5. So to solve for x, I would just do base stays base and the other two switch. Would probably be the fastest way. So e is my base. Now this whole thing would become my power. And it would equal the x, like that. Okay? So it's knowing that when you see that ln, that the base is e. Okay? It's like, rather than asking me what ln is, which I'm sure I will get asked about 3,000 times this year. Okay, so the other one here, if I'm changing this around, b here, I'm going to change it to a logarithm. What would be the base of my logarithm? E. And then what would be my log e part of my logarithm? Well, go inside the logarithm. 10. And that would equal 2x. And then I would just divide by 2. So this is ln 10. So instead of writing log e10, I would write ln 10 divided by 2 equals x. This is super not the same as ln 5. Okay? So please do not ever write ln 5. It's really not the same, super not the same. Don't do it. Ln 10 does not mean ln times 10, right? Like it does not mean that. So you cannot divide the 10. The 10 is stuck to the log and you can't do anything with it. Okay? And that's that. So try to stay familiar with that stuff. Man, I'm all out of order here. Thought I put that